Somewhere outside your window right now, the world looks completely normal. Maybe there are streets, buildings, maybe a coastline in the distance, maybe just fields stretching out to the horizon. Whatever you see, whatever you're imagining, I want you to know that roughly 20,000 years ago, a huge portion of it was buried under ice. Not a light frost, not a bad winter. A wall of glacial ice in some places over a mile thick, pressing down on the land with unimaginable weight, reshaping continents, locking up so much of the planet's water that sea levels were more than 400 feet lower than they are tonight. And then, somehow, it ended. Not all at once. Not smoothly, not in any way that the word thaw really does justice to. The end of the last ice age is one of the most dramatic, most consequential, and most misunderstood events in the entire history of our planet. And that's exactly what we're going to explore tonight. Before we go any further, tell me where you're listening from and what time it is where you are. Drop it in the comments. I read them, and every time I do, it genuinely amazes me. Someone in Edinburgh at 2 in the morning, someone in Melbourne just after dawn, someone in Sao Paulo with rain on the window. All of you falling asleep or trying to while we walk back through deep time together. I love that. So tell me where you are now. Close your eyes for a moment if that helps, and imagine the world not as it is, but as it was. It's around 21,000 years ago, the peak of the last glacial maximum, and Earth looks almost like a different planet. The British Isles are not islands at all. They're attached to mainland Europe by a broad plain of frozen tundra. Where the North Sea sits today, mammoths walked. Where the shallow waters off Siberia now lap quietly, there was a vast subcontinent connecting Asia to North America. People walked across it. They didn't know they were crossing between worlds, they were just following the animals. In North America, a sheet of ice, called the Laurentide, covered nearly the entire northern half of the continent. Where Chicago sits today, the ice was perhaps 2 miles deep. The Amazon basin was cooler and drier, more open savanna than the jungle we know. Australia's coastline extended hundreds of miles further out to sea, and across Africa, across the Middle East, across Central Asia, climates had shifted in ways that fundamentally changed what could live where and who could survive. This is the frozen world that stood on the edge of change. And here is the mystery at the heart of tonight's story. How fast did it all shift? The answer, it turns out, is both slower and faster than anyone expected, and the full picture is stranger and more dramatic than the simple phrase, "the ice age ended," suggests. Because here is the thing that scientists spent decades piecing together from ice cores and the end of the last ice age was not a single smooth warming trend. It was a series of surges and reversals, of sudden lurches forward into warmth and then shocking plunges back toward cold. There were periods when temperatures in Greenland rose by nearly 15 degrees Fahrenheit within a human lifetime, not over centuries, within decades, possibly faster. And then, just when the world seemed to be warming for good, something would trigger a dramatic cold snap that sent glaciers advancing again and plunged parts of the northern hemisphere back toward ice age conditions. The story we're going to tell tonight has several major threads, and they're all tangled together in ways that make it endlessly fascinating. There's the climate itself, swinging through changes so abrupt they would be terrifying to live through. There are the oceans rising and rising and rising as all that locked-up ice melted, flooding coastlines that people had been living on for generations, drowning lands that today lie under hundreds of feet of water. There are the ecosystems reshaping themselves almost faster than life could adapt, forests advancing north where tundra had been, grasslands shifting and shrinking, new habitats appearing in some places while ancient ones vanished forever, and running through all of it, making decisions and migrations and innovations in response to every change the climate threw at them, our people. Real people, in real places, facing a world in transformation. Some of their stories survive in the archaeological record, some survive in the genetic evidence written into our DNA, and some, tantalizingly, may survive in the flood myths and oral traditions that cultures all over the world have carried for thousands of years. Tonight, we're going to move through all of it, section by section, at whatever pace lets you drift comfortably between listening and sleep. There will be specific places and dates, there will be hard evidence, there will also be genuine mysteries, things scientists are still debating, questions the data hasn't fully answered yet. I'll tell you when we're on solid ground and when we're standing at the edge of what's known, looking out into what's still uncertain. But before we get into the mechanics of how we know any of this, I want to leave you with one image to hold on to as you settle in. Think about where you are right now, your town, your city, your coast, your countryside. Now imagine sea level dropping 400 feet. Picture the coastlines of the world pulling back from their current shores, new land appearing, new rivers crossing what is now open ocean. Somewhere near you, probably, there is a landscape that existed during the Ice Age that is now underwater. A valley, a plain. Maybe the remains of a camp where someone sat by a fire and looked at a sky full of stars. That world is still there, preserved under cold water in the dark, waiting to be found. We don't fully know what happened in those submerged places. We don't know all the names that people gave to rivers that no longer exist, or coastlines that vanished beneath the rising sea. But we're learning slowly, piece by piece, from sediment cores and sonar scans and ancient DNA and frozen insects preserved in ice. We are reconstructing the night the world started to thaw, and it turns out it was one of the most eventful nights our species has ever lived through. So how do we actually know any of this? How does a scientist sitting in a laboratory in the present moment look back 20,000 years and say with genuine confidence that a glacier was retreating here, that the temperature was rising there, that a forest was replacing a grassland in a place where no human being wrote anything down, where no calendar was kept, where the only record that survives is buried in rock and ice and sediment? The answer is that the Earth kept its own records, not in language, not in anything we wrote, but in chemistry, in biology, in the physical signatures that climate leaves behind in the materials of the world. And once scientists figured out how to read those signatures, the past opened up in extraordinary detail. The most famous of these records are the ice cores. You've probably heard the phrase, but here's what it actually means. In Greenland and Antarctica, snow has been falling and compressing into ice for hundreds of thousands of years. Each year's snowfall traps a thin layer of atmosphere, a snapshot of the air as it existed at that moment, sealed inside the ice like a message in a bottle. When scientists drill down through that ice and pull up a core, they're pulling up a timeline. They can count the annual layers the way you count tree rings, and buried inside each layer are tiny bubbles of ancient air. Those bubbles contain ancient carbon dioxide, ancient methane, ancient traces of volcanic ash that can be matched to specific eruptions, but the most powerful information comes from the water molecules themselves, specifically from what are called oxygen isotopes. Water is mostly made of ordinary oxygen-16, but a small fraction contains heavier oxygen-18. The ratio of these two isotopes in any given layer of ice tells you something precise and remarkable. It tells you approximately what temperature the atmosphere was when that snow fell. Colder air produces snow that is lighter in oxygen-18. Warmer air produces snow that is heavier. Read those ratios down through thousands of meters of ice, and you get a temperature record of breathtaking precision, stretching back across hundreds of thousands of years. The ice cores from Greenland and Antarctica don't always tell exactly the same story, and that's actually important. It tells us that climate change during the last glacial period was not uniform. The northern and southern hemispheres sometimes warmed and cooled on slightly different schedules, which says something profound about the ocean currents and atmospheric systems that drive climate. The picture is not simple. It never was. But ice cores can only take you so far, literally. They exist where ice has accumulated and stayed frozen. For the rest of the world, you need other archives, and there are many. Pollen is one of the most intimate. Every flowering plant produces pollen grains that are almost indestructible. When pollen settles into a lake bed or a peat bog, it gets buried in sediment, layer by layer, year by year. Core that sediment, analyze the pollen at each depth, and you get a detailed picture of what plants were growing in that region at that time. Oak pollen tells you there were oak trees. Grass pollen tells you there were grasslands. Pine, birch, sedge. Each species leaves its own signature, and shifts in those signatures mark the arrival of new climates. In Britain, for example, the pollen record shows the moment when tundra grasses gave way to birch scrub and then to dense oak woodland, tracking the warming as precisely as a thermometer. In North Africa, it shows lakes that existed in what is now deep Sahara Desert, surrounded by reeds and grassland, and then the slow disappearance of that world as conditions dried again. Lake sediments contain other signals too. The chemistry of the sediment itself, the types of algae preserved within it, even the tiny shells of single-celled organisms called diatoms all respond to temperature and rainfall and ice cover in ways that scientists have learned to decode. Every lake basin is essentially a slow-motion recorder, accumulating evidence year after year, century after century, preserving a local climate history in its mud. Then there are speleothems, the stalactites and stalagmites that grow inside caves. They grow as water drips through limestone, depositing thin layers of calcium carbonate over long periods of time. Like ice and sediment, they build up in layers, and like ice cores, those layers carry oxygen isotope signatures that reflect the temperature and rainfall conditions when each layer formed. Caves in China, in France, in the Bahamas, in Brazil have all yielded speleothem records that match and cross-check the ice core data, confirming warming periods and cold snaps and helping to build a global picture from dozens of local sources. On the landscape itself, glaciers left physical signatures that are still visible today. When a glacier sits in one place long enough, it pushes a ridge of rocks and debris ahead of it called a moraine. When the glacier retreats, the moraine is left behind like a scar on the land. Geologists can map those moraines, trace the former extent of ice sheets, and by dating the organic material trapped within the moraines, reconstruct how far glaciers reached at different points in time. That brings us to dating, because knowing what happened is only half the challenge. Knowing when it happened is where things get genuinely complicated, and where honest scientists will tell you the picture has real limits. The most widely used method is radiocarbon dating. Living organisms absorb carbon dioxide, including a radioactive form called carbon-14, which forms constantly in the upper atmosphere. When an organism dies, it stops absorbing new carbon, and the carbon-14 it contains begins to decay at a known rate. Measure how much is left, and you can calculate how long ago the organism died. It works on wood, bone, charcoal, shell, seeds, the organic material preserved in sediment layers. It's remarkably powerful, but it has a hard ceiling. After about 50,000 years, so much carbon-14 has decayed that reliable measurement becomes nearly impossible, and the signal disappears into noise. There's also a subtler problem. The amount of carbon-14 in the atmosphere hasn't been constant through time. It fluctuates with solar activity and changes in ocean circulation. This means that raw radiocarbon dates don't perfectly correspond to calendar years. Scientists have spent decades building calibration curves, using tree rings and coral records and lake valves to translate radiocarbon years into real years. And those calibration curves are genuinely good now, far better than they were a generation ago. But there are still regions of uncertainty, especially as you push back toward and beyond 20,000 years ago. When you hear scientists debate exactly when a particular glacier retreated or a particular warming event peaked, those calibration issues are often part of what's actually being argued. For events and materials that lie beyond radiocarbon's reach, other methods take over. Uranium-thorium dating works on speleothems and corals over much longer time scales. Cosmogenic nuclide dating can tell you when a boulder was first exposed to the sky by a retreating glacier. Luminescence dating measures when sediment grains were last exposed to light. Each method has its own strengths and its own uncertainties, and when multiple methods agree, confidence goes up considerably. Sea level itself has become a powerful recorder. As ice sheets melted, ocean waters rose and flooded coastlines. Those old shorelines didn't entirely disappear. In some places, they're preserved as coral reef terraces, ancient reefs that grew at sea level and then were stranded as the land or the sea surface changed position. In tropical regions like Barbados and the Huon Peninsula of Papua New Guinea, sequences of these fossil terraces act like a staircase marking the sea level at different moments going back hundreds of thousands of years. They provide some of the most direct evidence we have for how fast ocean levels rose and when the major pulses of melting occurred. Drowned shorelines are equally telling, though harder to read. Sonar surveys of continental shelves have revealed submerged river valleys, estuary systems, even the faint traces of ancient beaches now lying under dozens or hundreds of feet of water. These features confirm that sea levels really were dramatically lower during the glacial maximum, and they hint at the coastal landscapes, and possibly the settlements, that the rising ocean swallowed. But here is what all of this evidence together cannot yet do perfectly. It cannot give every region of the world the same resolution or the same certainty. Ice cores from Greenland tell us the northern Atlantic story with extraordinary precision. But Central Africa, the interior of South America, large parts of Southeast Asia, these regions have thinner records, fewer sites, more gaps. The timeline of the Ice Age's end looks different depending on where you're asking about it. Some regions warmed early and fast, others stayed cold longer. Some went through the warming and then snapped back into severe cold while others didn't. Debating the timing of specific events is not scientists being indecisive. It reflects the genuine complexity of a planet where climate changes don't arrive everywhere at once. What all of it confirms, from ice cores to pollen to moraines to drowned reefs, is that something immense and consequential happened. The frozen world of 21,000 years ago became the world we know, and the how and the when of that transformation, the surges and the reversals, the pulses of warmth and cold, that is the story we're just beginning to tell. If you follow those records back to their coldest point, they converge on a particular moment. Not a single year, of course, but a window in time. Somewhere around 26 to 19,000 years ago, depending on which dataset you look at, the planet slipped into what climatologists call the last glacial maximum. This was as close as our world has come in recent geological history to being a different planet. In the north, an ice sheet the size of a continent sat on top of Canada and the northern United States. The Laurentide ice sheet, as geologists call it, was in places more than 2 miles thick. Its southern edge reached down into what is now New York, Ohio, Illinois. Another great mass of ice, the Cordilleran ice sheet, lay draped over the mountains of western North America. Across the Atlantic, the Fennoscandian ice sheet buried Scandinavia, much of Britain, and parts of northern Germany and Poland beneath a continuous slab of ice. Glaciers locked up the Alps, the Pyrenees, the Carpathians, the Caucasus. In the southern hemisphere, the great Patagonian icefields pushed further north, and mountain glaciers in New Zealand and on high African peaks grew far larger than they are today. Between and around these frozen fortresses stretched a different kind of landscape. A continuous belt of steppe tundra, sometimes called the Mammoth Steppe, ran from Western Europe across Siberia and into Beringia, the land bridge that then connected Asia and North America. It was a strange, productive, cold grassland, not the empty white wasteland we often picture when we say Ice Age, but a rolling, wind-swept expanse of short grasses, sedges, herbs, and low shrubs. Trees were rare away from sheltered river valleys and coasts. The air was dry, the winds strong, the winters long and bitter, but the summers, brief and bright, could burst into carpets of flowers and forage. Global temperatures were lower, maybe 4 to 6 degrees Celsius cooler on average than today. But that number hides brutal regional contrasts, much colder over the big ice sheets. Colder, drier, windier almost everywhere mid-latitude, the oceans were cooler, tropical rain belts had shifted, monsoon systems weakened or moved, leaving some regions that are now lush, sharply drier, and making others unexpectedly greener. So much water was locked up in ice that the level of the world ocean fell by roughly 120 meters, nearly 400 feet. Coastlines were not where you see them on a modern map. Broad shelves around continents, which today sit underwater, were then dry land. The North Sea basin between Britain and mainland Europe was an exposed plain crisscrossed by rivers, a region archaeologists call Doggerland for the fishing bank that now covers a fragment of it. You could have walked from what is now the English Midlands across gentle lowlands to what is now Denmark without ever seeing an open ocean. The Sunda Shelf joined mainland Southeast Asia to the islands of Borneo, Java and Sumatra, forming a single large peninsula we call Sunderland. To the north, the Sahel Shelf connected New Guinea, Australia and Tasmania into a single landmass. Beringia, stretching between Siberia and Alaska, was not a narrow isthmus but an enormous, cold, grassy subcontinent. Rivers ran longer courses across these expanded continental margins. Deltas stood far out from the present shoreline, estuaries, lagoons, wide coastal plains, and what may have been rich human and animal habitats now lie drowned beneath shallow seas. The atmosphere that moved over this altered planet did not behave quite the way it does today, with huge ice sheets rising like cold mountain ranges. The jet streams, the bands of strong winds high in the atmosphere shifted in latitude and strength. Storm tracks wrapped differently around the hemispheres. The contrast between icy high latitudes and warmer tropics sharpened certain pressure systems, while the sheer dryness above the ice changed how clouds formed and where rain fell. One result was dust, a lot of dust. Ice cores from Antarctica and Greenland show that during the last glacial maximum, the air carried far more fine mineral particles than it does today. In some intervals, the dust flux recorded in Antarctic ice is an order of magnitude higher. Exposed continental shelves, dried-out lakebeds, and sparsely vegetated plains all became easy sources for wind-blown silt. Each winter, cold winds scoured these surfaces and lofted dust into the atmosphere, where it could travel thousands of kilometers before settling out over ice sheets, oceans, and distant land. That dust dimmed some skies, fertilized others. When it fell into the oceans, it carried iron and other nutrients, stimulating blooms of microscopic algae. Those algae drew carbon from the surface waters, and when they died, some of that carbon sank. Climate scientists still debate how large a role this giant dusty fertilization experiment played in maintaining lower atmospheric carbon dioxide during the glacial maximum. But the connection is there, a colder, dustier world with lower greenhouse gas concentrations than the one you live in. Within this framework of ice, grassland and dust, life did not simply endure. It adapted, diversified, and in some cases thrived. The Mammoth Steppe supported enormous herds of grazers and browsers, mammoths, woolly rhinoceroses, wild horses, steppe bison, saiga antelope, musk oxen, giant deer with antlers like living trees. Predators stalked among them, cave lions, scimitar-toothed cats in some regions, packs of wolves and hyenas, bears both brown and giant. Many of these animals carried dense coats, compact bodies, short extremities, and specialized fat deposits, textbook adaptations to conserve heat in frigid environments. Others relied on mobility, moving long distances in search of grazing that had not yet been stripped bare by previous herds. Humans, too, were part of these cold-adapted ecosystems. In Europe and Western Asia, Neanderthals and later modern humans used caves and rock shelters for protection from the wind, built substantial hearths, and clothed themselves in carefully prepared animal skins. Archaeological sites from France to Ukraine preserve the remains of mammoth bone structures, rings and ovals of tusks and long bones that may have formed the frames of dwellings, insulated with hides and turf. Farther east, in Siberia, hunter-gatherers followed reindeer, horses, and mammoths across the open steppe, timing their movements with seasonal migrations at Farther east, in Siberia, hunter-gatherers followed reindeer, horses, and mammoths across the open steppe, timing their movements with seasonal migrations. In Africa, the picture was different but equally demanding. The great equatorial ice sheets never formed there, but cooler temperatures and altered rainfall patterns reshaped the continent. Some regions became more open and arid, with grasslands expanding at the expense of forest. Other areas contracted into refuges of moisture and greenery, where rivers, lakes, or coastal upwelling kept local ecosystems relatively rich. It was within these fluctuating African landscapes that the ancestors of modern humans, already fully anatomically modern, refined the flexibility. Coral reefs grew at lower sea levels along the margins of exposed shelves. Mangroves colonized new river mouths. Even at the equator, the last glacial maximum was not simply business as usual, with slightly cooler air. It was a wholesale rearrangement of seasonal rhythms, rainfall belts, and coastlines. When you zoom out, the last glacial maximum can look deceptively stable. On a graph, temperatures appear to flatten near their coldest values. Ice volumes peak and then hold more or less for several thousand years. Vegetation maps drawn from pollen show tundra, steppe, and sparse woodland locked into place across vast regions. The climate system, after tens of thousands of years of gradual cooling, seems to pause there, as if it has finally settled into a long, deep freeze. But stability in climate science is often a kind of balance on a knife edge. The very size of the ice sheets made them sensitive. Their sheer weight depressed the crust beneath them. Their bright surfaces bounced enormous amounts of solar energy back into space. Their margins lay close to the latitudes where seasonal melting could nibble at them each summer. Ocean currents were rerouted by changes in salinity and temperature. The atmosphere held less carbon dioxide and methane than today, but not so little that further changes were impossible. From the vantage point of someone living then, the world might have seemed eternal, the huge white horizons, the dry winds, the familiar migrations of animals, the long dark winters, and short intense summers repeating in a recognizable pattern. From the vantage point of the geological record, that apparent permanence was an illusion. The system was primed. The ice sheets, oceans, and atmosphere were poised so that relatively small shifts in sunlight distribution, greenhouse gas concentrations, or ocean circulation could start a cascade. The last glacial world at its peak was not just an ending, a culmination of cold, it was a loaded spring. In the sediments and the ice cores, you can see the first tiny hints that the balance was about to change. A faint uptick in greenhouse gases, subtle warming in some regions, minor retreats and re-advances of glacier fronts. Nothing that would have been obvious to a hunter looking out over a frozen river, but enough to tell us from our distance that this apparently frozen planet was already beginning to move toward its next state. The stage was set, the oceans were low, the ice piled high, the winds full of dust, the ecosystems tuned to cold. The world looked stable. Underneath it was ready to thaw. The first signs in the record look almost disappointingly small. A fraction of a degree here, a few parts per million of carbon dioxide there. A little less dust in one ice core, a slight shift in the timing of melt layers in another. If you compress 20,000 years into a single line on a graph, the end of the last glacial maximum doesn't begin with a sharp corner. It begins with a slow, almost reluctant bend. Sometime around 19 to 18,000 years ago, depending on which proxy you trust, that bend becomes clear. The great ice sheets are still immense, sea level is still far below modern, winters are still long and brutal across much of the northern hemisphere. But the loaded spring the climate system has been balanced on begins, at last, to release. To understand why, you have to follow the sun. Earth does not go around the sun in a perfectly stable way. Its orbit and its tilt wobble and stretch in slow, predictable cycles, driven by the gravitational pull of the moon, the other planets, and the shape of the orbit itself. These are the so-called Milankovitch cycles, changes in eccentricity, obliquity, and precession. Those names sound like they belong to an astronomy textbook, but you can think of them more simply as three slow adjustments to how sunlight is distributed over the planet. Eccentricity is about shape, how circular or oval Earth's orbit is over roughly 100,000-year periods. The orbit becomes slightly more elongated, then more circular again. Obliquity is about tilt, the angle between Earth's rotational axis and the line perpendicular to its orbit. Over about 40,000 years, that tilt rocks gently back and forth by a couple of degrees. Precession is about direction, the slow wobble of Earth's spin axis, like a top about to fall, which changes where in the orbit each season occurs on cycles of roughly 19 to 23,000 years. Individually, these changes do not dramatically alter the total energy Earth receives from the Sun across a full year. The average, integrated over the whole globe and all seasons, stays almost the same. That's one of the strange truths of ice ages. They are not, in any simple sense, caused by big swings in total sunlight. What changes instead is when and where that sunlight arrives. Summer at high northern latitudes is the key. Giant ice sheets are built in the north on land, where snow can pile up and compact into ice without sliding into the sea. For those ice sheets to grow, summers must be cool enough that much of the winter snowfall survives. For them to shrink, summers must be warm and long enough to melt more snow than falls. Orbital forcing, as climatologists call it, works by adjusting the intensity of summer sunshine above about 40 to 60 degrees north. When Earth's tilt is greater and precession lines northern summer up with the part of the orbit where Earth is closer to the Sun, high-latitude summers receive more energy. When tilt is smaller and summer lines up with a more distant part of the orbit, those summers receive less. During the build-up to the last glacial maximum, high-latitude northern summers had been, on average, weak. Snow that fell in winter lingered. Over tens of thousands of years, that small seasonal imbalance allowed ice sheets to advance. By around 20,000 years ago, the orbital geometry had shifted. The pattern of tilt and wobble began to favor stronger northern summers again. Not everywhere, not all at once, but enough that on average the peak summer sunlight over northern ice changed by tens of watts per square meter, large compared with the gentle nudges climate usually experiences. From the perspective of someone living on the Mammoth Steppe, this would not have been obvious in a single lifetime. A certain river melting a few days earlier in spring, a patch of ground near the ice front that now stayed bare all summer instead of holding onto a snowbank. Tiny local signs buried in the noise of year-to-year weather. From the perspective of the ice sheets, it mattered. Warmer, brighter summers at their southern margins nudged the balance. More meltwater ran off. The snow line climbed. Exposed dark rock and soil absorbed more solar energy than the reflective ice and snow they replaced, amplifying the local warming. The edge of the ice began to creep back, but orbital forcing alone, most climate scientists agree, cannot explain the full magnitude of the deglacial warming. The change in seasonal sunlight starts the process. Something else helps carry it forward and spread it globally. Here is where greenhouse gases enter the story. In Antarctic ice cores, you can see atmospheric carbon dioxide begin to rise from its glacial low of around 180, 190 parts per million toward its modern pre-industrial value of about 280. The initial uptick begins roughly in step with the first hints of Southern Ocean warming, perhaps slightly earlier or later depending on which record you line up and how you synchronize the timescales. Methane, measured in the same bubbles, also climbs from about 350-400 parts per billion to around 700. Neither increase happens all at once. They come in steps and plateaus, with pauses where the climate briefly cools again and surges where warming accelerates. Why did CO2 and methane rise? That, even now, is not entirely settled. One widely studied idea focuses on the Southern Ocean, the ring of cold, deep water encircling Antarctica. During the glacial maximum, stronger winds, more sea ice, and different circulation patterns may have trapped more carbon in the deep ocean, away from the atmosphere. As the orbital configuration shifted and some regions began to warm, sea ice around Antarctica thinned and retreated. Winds adjusted, upwelling currents brought deep carbon-rich waters back toward the surface. There, in contact with the air, some of that dissolved carbon dioxide escaped. Another line of thinking emphasizes the role of biological and chemical changes as dust flux declined. For instance, iron fertilization of some ocean regions may have weakened, reducing the capacity of surface algae to draw down carbon. Shifts in nutrient supply, ocean stratification, and sea ice cover all could have tweaked the delicate balance of carbon exchange between ocean and atmosphere. Methane likely responded to changes on land as well as in the tropics. As ice margins retreated and permafrost in some regions began to thaw, wetlands expanded in certain belts. Warmer, wetter conditions in monsoon regions and tropical lowlands could have increased the area of bogs, floodplains, and marshes, natural methane factories where microbes break down organic matter in oxygen-poor waterlogged soils. None of these processes act in isolation. Each interacts with the others. A small warming at high northern latitudes, initiated by orbital changes, can alter winds and ocean currents, which adjust sea ice, which shifts where deep ocean water surfaces, which changes how much CO2 is exchanged with the atmosphere, which then alters global temperatures a bit more. And crucially, the response is not identical in both hemispheres. Antarctic ice cores show a relatively smooth, gradual warming from about 19,000 years ago onward, punctuated by a few notable pauses. Greenland ice cores, in contrast, record more abrupt jumps. Northern temperatures can leap in a few decades or centuries, then stall, then fall back, as large-scale ocean circulation reorganizes itself. One popular way of framing this difference is in terms of the Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream and the sinking of cold, salty water in the North Atlantic. As fresh water from melting ice enters the North Atlantic, it can, in some models and reconstructions, weaken that sinking. When it weakens, less heat is carried northward by the ocean, cooling parts of the northern hemisphere, and paradoxically allowing the south to warm more. In this view, the deglaciation is a kind of hemispheric seesaw. Orbital changes gradually increase northern summer sunlight, nudging the ice to melt. That meltwater occasionally disrupts ocean currents enough to cool the north, even as the south continues to warm, shifting where heat is stored and how quickly each region responds. But the exact sequence of cause and effect is still debated. Do southern ocean changes drive the initial CO2 release, which then warms the whole planet, including the north? Or do northern ice sheets begin retreating under orbital forcing, altering ocean circulation in a way that eventually leads to southern ocean ventilation? Are methane increases mainly a response to warming? Or do they help trigger some of the rapid jumps by adding their own extra push? Aligning the timelines of different records, Greenland ice, Antarctic ice, deep-sea sediments, cave stalagmites, glacial moraines on land, is not trivial. Each archive has its own dating uncertainties, its own lags between cause and recorded effect. Different groups, using different methods, produce subtly different chronologies. From those differences emerge competing narratives about who leads and who follows in the great deglacial dance. What is consistently clear, though, is the pattern. A shift in the distribution of sunlight, focused on northern summers, followed by a multi-millennial rise in greenhouse gases, accompanied by hemispherically uneven warming, interrupted by abrupt cold relapses. From the human perspective, this first great warming was slow enough to span many hundreds of generations, yet fast enough to transform coastlines, ecosystems, and migration routes within the memory of oral traditions. From the climate system's perspective, it was a rapid transition from one stable state to another, amplified by feedbacks it had itself set in motion. The ice had begun to loosen its grip. Under rising skies and lengthening thaws, the great sheets of frozen water that had reshaped continents for tens of thousands of years started, very slowly, to move. When most people imagine an ice sheet disappearing, they picture it like a block of ice on a countertop. The room warms. The block sits there, and a uniform puddle slowly spreads around it until nothing is left. Real ice sheets are nothing like that. They are not blocks. They are slow rivers, thousands of meters thick, spread across whole continents. They flow, they crack, they surge forward even as they thin and retreat. They obey gravity and friction and the strange counterintuitive physics of ice under pressure. As summers strengthen and greenhouse gases rise, the first response of a giant ice sheet is not to politely shrink in place. It begins to move differently. At its surface, more snow turns to meltwater. Some of that water runs off, some finds crevasses and moulins, vertical shafts in the ice, where it plunges down toward the bed. When enough water reaches the base, it can lift parts of the ice sheet slightly off the rock, reducing friction. A glacier that was grinding forward a few tens of meters per year can suddenly lurch ahead in a surge, sliding on a thin, pressurized film of water and deforming the sediment beneath it like wet clay. So, while the overall margin of the ice may be retreating northward, locally the ice can pulse forward, overrunning its own retreat line, bulldozing rock and soil, then collapsing back as warmth wins again. The boundary between ice and no ice does not move like a clean, steady front. It flickers, stalls, jumps. The record of those pulses is carved into the landscape. Ahead of the ice, meltwater seeks escape paths. At the peak of glaciation, many of those paths are blocked by frozen walls hundreds of meters high. Rivers that once flowed freely are dammed by ice. Valleys flood. Vast proglacial lakes form lakes not hemmed in by stone, but by ice itself. Some of these lakes were modest, filling a lowland or backing up behind a lobe of glacier for a few centuries before spilling over into a neighboring basin. Others were enormous by any standard. In North America, meltwater pooled in basins that had been scoured deeper by the Laurentide ice sheet. One of them, often called Lake Agassiz in the geological literature, may at times have held more liquid water than all the modern Great Lakes combined. In Eurasia, Massive lakes formed south of the retreating Scandinavian ice, linking and unlinking drainage basins that are now separate. These lakes were not stable, placid features. As the ice margin twitched, the level of the lake rose and fell. If the ice dam at one end thinned and floated, water could begin to seep under it. If the dam fractured along a hidden weakness, an outlet could open catastrophically. Imagine billions of tons of water, held tens or hundreds of meters above sea level, suddenly finding a lower path to the ocean. In some reconstructions, these outburst floods may have drained entire proglacial lakes in a matter of weeks or months, sending torrents across the land at flows that dwarf any modern river. They carved spillways, stripped soil from bedrock, rearranged drainage networks. In places like the channeled scablands of the northwestern United States, the scars of such floods, deep coulees, giant ripples, isolated rock mesas, can still be traced. Each time an ice dam failed, the downstream world changed. Sediment that had been trapped in quiet lake bottoms was swept away or dumped in new deltas. Rivers were forced into new courses. Wetlands and floodplains blinked in and out of existence on timescales human groups could feel in a lifetime. And all the while, beneath the bending ice, the land itself was moving. An ice sheet 2 or 3 kilometers thick weighs enough to push the crust of the earth down by hundreds of meters. Over tens of thousands of years, under that steady load, the rock and the underlying mantle deform. The land flexes like a very slow, very stiff trampoline. When the ice begins to thin and retreat, that pressure eases. But the solid earth does not spring back instantly. It responds over centuries and millennia, flowing and relaxing like extremely viscous honey. This delayed response is called isostatic rebound. In regions that had been at the center of the great ice sheets, parts of Canada, Scandinavia, and northern Britain, the land surface began, imperceptibly, to rise. At first, the rate might have been a few millimeters a year, then, in some places, centimeters. Over the full deglacial period, that rebound could total hundreds of meters of uplift. From the point of view of an early human camped near the shore of a glacial sea, the effect would be subtle but real. A cove that once took a short walk to reach might, generations later, require a longer trek. Former beaches, with their shells and driftwood, would now sit as raised terraces above the tide. Rivers that once flowed sluggishly into a drowned valley would find their gradients steepened as the land tilted. Cutting new channels, rebound did not happen uniformly. Places where the ice had been thickest rose the most. Peripheral areas, which had bulged upward slightly under the weight pushed elsewhere, actually subsided. Coastlines warped, tilting entire regions so that some shores seemed to emerge from the water while others drowned. In that sense, the end of the Ice Age was not only about ice vanishing, it was about continents subtly changing shape. These shifting surfaces had direct consequences for future ecosystems and for any humans trying to navigate them. As ice lobes pulled back from valleys, they left behind thick blankets of till and outwash, unsorted mixes of clay, sand, gravel, and boulders, and vast plains of finer sediment washed from the melting front. On top of freshly exposed bedrock, thin, stony soils could take centuries or longer to accumulate. On glacial outwash plains and former lake bottoms, in contrast, deep, well-drained, mineral-rich soils formed relatively quickly. Where good soils developed, plants followed. First hardy pioneers, then shrubs, then forests and grasslands. The pattern of retreat, the routes meltwater took, the places lakes occupied and then abandoned. All of it helped judging which valleys would become fertile corridors and which would remain barren for longer. For animals and humans moving across these emerging landscapes, the effects were profound. Some former ice-blocked routes suddenly opened as passable corridors. A low pass between mountains, a newly drained valley, a river bent into a more accessible course. Others closed as rebound lifted land above a shallow seaway or as a lake expanded behind some remaining ice plug. Even before global sea level is considered, the map was already in flux. But the ice did not only rearrange rivers and soils. Every surge, every episode of accelerated melt, every catastrophic lake drainage poured fresh water into the oceans. Those pulses of meltwater, superimposed on the long, slow background of deglaciation, changed sea level and, with it, ocean circulation. When a giant proglacial lake found a new outlet to the sea, downstream salinity in the receiving basin could drop noticeably. In the North Atlantic, episodes like this are often linked to sudden slowdowns of the overturning circulation you met in the previous section. Each slowdown reshuffled where heat was stored, nudged storm tracks, and altered regional climates for centuries. So, the story of ice sheets on the move is not just a tale of melting. It is a story of dynamic, restless ice, reorganizing the hydrology of continents, flexing the ground beneath it, and sending pulses of water that tugged on the entire climate system. By the time the great continental glaciers had retreated far toward the poles, the world's rivers, shorelines, and future migration paths were already being redrawn. What remained was for the oceans themselves to catch up. By the time the oceans began their real rise, the land had already started to rearrange itself. Ice had withdrawn from many valleys. Proglacial lakes had come and gone. Rivers had been bent, diverted, sometimes erased. Isostatic rebound was tilting whole regions, lifting some coasts and letting others sag. Onto this shifting stage, the seas advanced. At the height of the last glacial maximum, global sea level was somewhere around 120 meters lower than today. Not a gentle dip, not a few extra beaches exposed at low tide, but a wholesale redraw of the world map. Continental shelves that are now drowned under shallow seas stood exposed as broad, habitable plains. The North Sea basin was dry land, crossed by rivers that joined the Thames and the Rhine into a single drainage flowing toward a far-off Atlantic shore. Between what is now mainland Asia and the scattered islands of Southeast Asia, wide stretches of land, Sunderland, linked modern Borneo, Java, Sumatra, and the Malay Peninsula. To the north, a broad steppe known as Beringia connected Siberia and Alaska, its rivers meandering through a cold but productive grassland. As ice melted, all of those landscapes began to sink, not because the land moved, but because the water rose. If you could watch a time-lapse of the last 20,000 years from orbit, you would see the shorelines creep inland, hesitate, then surge. River mouths would drown, turning into estuaries. Low saddles between islands would vanish under shallow channels. Some islands would appear for a while as hilltops on a shrinking shelf, then themselves disappear beneath the waves. On average, across the full deglaciation, global sea level rose at something like a centimeter or less per year. That sounds almost calm, but averages blur the drama. The rise did not happen as a smooth, even slope. It came in fits and starts, with long intervals of modest change punctuated by sharp jumps. Intervals geologists sometimes call meltwater pulses. The reason lies back with the ice sheets. So long as most glaciers were cold, thick and stable, melt was slow. As warming intensified, thresholds were crossed. Ice margins retreated into basins where their fronts floated on water. Ice shelves that had buttressed inland ice thinned and collapsed. Proglacial lakes found new lower outlets and dumped their contents seaward. In some reconstructions, whole sectors of ice sheets may have destabilized and flowed rapidly into the ocean over a few centuries. From the ocean's perspective, each of these events was a sudden addition of fresh water stacked on top of the slow background drip. The geological record keeps score, far from the former ice sheets, on subsiding tropical margins where isostatic rebound is minimal. Coral reefs grew toward the light as sea level rose. Corals have strict limits, they live within a narrow band of water depth. By drilling through ancient reef terraces and dating the skeleton, they show intervals where reefs kept pace with a few millimeters of rise per year, and others where the rate of deepening surged to several centimeters per year or more, too fast, in some places, for corals to keep up. One of the most discussed episodes occurs around 14,500 years ago. In some reconstructions, sea level may have climbed on the order of 20 meters within a few centuries, an event often labeled Meltwater Pulse 1A. There is active debate about the exact magnitude and timing, about which ice sheets supplied the water, and about how uniform the effect was across the globe. Some records show a dramatic jump, others suggest a more modest, drawn-out rise. What most lines of evidence agree on is that there were moments when coastlines moved faster than usual, fast enough that a child might hear stories from elders about a bay that had been smaller in their youth, and their own children might see that bay extend even farther inland. Locally, the story was even more complex. Global sea level is just the average of many regional seas, each responding not only to the volume of water, but to gravity and the shape of the Earth itself. A massive ice sheet does more than press down the crust beneath it. It also exerts a gravitational pull on the surrounding ocean, tugging water toward it, raising sea level along its margin. As an ice sheet shrinks, that pull weakens. Water that had been heaped up near the ice edges flows away toward the open oceans. Close to the former ice, sea level can actually fall for a time even as the global average is rising. Farther away, the opposite happens. Sea level rises more than the global mean as the redistributed water finds new equilibrium. Add in ongoing isostatic rebound and small shifts in the Earth's rotation as mass moves around, and you get a patchwork of changing coastlines. Some regions experienced relatively gentle, gradual drowning. Others saw shorelines racing inland across low plains, eating away kilometers of land in a human lifetime. As the sea advanced over those plains, new worlds formed at the fringe. River mouths, no longer able to carry sediment out to a distant shelf edge, began to drop their loads close to shore, building deltas that crept outward, even as the general trend of the sea was landward. Freshwater met saltwater in shifting zones where tides pushed inland and floods pushed seaward. These mixing zones, estuaries, became nurseries for fish, cranes, and countless invertebrates. Behind barrier spits and sandbars reworked by waves, shallow lagoons formed. Marsh grasses colonized the quieter corners. Peat began to accumulate. Migratory birds learned new resting spots. For humans, these estuaries and wetlands would one day be magnets, rich in shellfish, fish, reeds, and game. But for every new estuary created, something was erased. Those broad continental shelves had not been empty during the glacial maximum. They were dry land, with rivers, lakes, and very likely people. Wherever there was access to fresh water, to migrating herds, to coastal resources at the old lower shorelines, human groups would have camped, hunted, gathered, perhaps lingered long enough to leave hearths, tools, and stories. As sea level rose, those camps and pathways would have been abandoned in stages. First seasonally flooded, then only used at certain times of year, finally submerged entirely beneath the advancing surf. From an archaeological perspective, this is a quiet catastrophe. The record of human life near the coasts during the late Ice Age and early deglaciation is, to an unknown but likely large extent, underwater. Some estimates suggest that a substantial fraction of all the places humans once lived between about 20,000 and 7,000 years ago now lie on drowned shelves, beneath tens of meters of seawater. A handful of sites, discovered by chance or through systematic underwater survey, offer hints. Stone tools in now submerged channels off northern Europe, possible hearths and artifacts on the floor of the North Sea, once part of a landscape sometimes called Doggerland, traces of ancient shorelines and possible habitation off the coasts of Australia, Japan, the Americas. These finds are difficult and expensive to explore. Currents, sediment cover, and depth all conspire to hide the past. Many submerged landscapes remain only faintly mapped. As a result, our picture of human responses to the first great coastal floods is almost certainly incomplete. We can infer patterns. We can model how fast a given plain would have drowned, how rivers would have regraded, where new shorelines would have formed. We can imagine groups tracking the retreating coasts, inheriting stories about land out there that their grandparents had walked on. But the detailed evidence, the footprints, the discarded tools, the bones left beside a cooking fire, often lies beyond the reach of ordinary excavation. So when we talk about the end of the Ice Age and the rise of the seas, we are talking partly about a visible transformation and partly about an invisible one. Visible in the sense that the map we know today emerged from that time. The separation of Britain from Europe as the English Channel filled, the drowning of Beringia to leave a narrow Bering Strait, the flooding of Sunderland to create the island chains of Indonesia and the shallow South China Sea. Invisible in the sense that entire chapters of human adaptation to those transformations sank with the lands themselves. For the people who lived through it, though the experience would not have been a historical abstraction, it would have been the slow, uneasy feeling that the familiar edges of the world were moving. Fishing spots became deeper. A sandbar used for crossing a channel was suddenly gone. A fresh spring near the old shoreline now lay under brackish water. Sacred places perched on headlands became true islands. Generation after generation, the sea crept closer, step by irregular step, following the delayed promise of melting ice. And then, just as coastlines seemed to be in full retreat, another surprise emerged from the climate system, a sudden return of the cold. It began quietly, almost in defiance of the overall trend. The ice sheets were still retreating, the seas were still rising, but somewhere around 12,900 years ago, in parts of the northern hemisphere, the long thaw faltered, winters sharpened, summers weakened, glaciers that had been shrinking paused, and in some places began to grow again. In Greenland ice cores, the isotopic signature of temperature drops like a cliff. Within a human lifetime, maybe within a single generation, conditions in the North Atlantic world snapped back towards something much closer to glacial. This episode has a name, the Younger Dryas. The Dryas part comes from a small, hardy flower, Dryas octopetala, that likes cold, open tundra. Its pollen shows up in lake sediments across Europe in layers that mark earlier cold spells, the older and oldest Dryas periods. When the last of these sudden chills arrived, very late in the deglaciation, it became the younger one. From a global perspective, the Younger Dryas was not a simple, uniform plunge back into the Ice Age. Temperatures in the southern hemisphere did not drop in lockstep. Tropical oceans, buffered by their vast heat content, show more subdued changes. But around the North Atlantic Basin in Greenland, Northern Europe, Eastern North America, parts of Western Asia, the signal is unmistakable. Dust content in ice cores rises, a sign of drier, windier conditions. Ratios of oxygen isotopes shift, indicating colder air over Greenland. In many lake and bog sediments, warm-adapted trees retreat in the microfossil record, replaced by pollen from grasses, herbs, and that tough little dryas flower. The question, then and now, is why? One leading hypothesis centers on fresh water. As the great North American ice sheet melted, it did not just add water steadily to the oceans, it also created enormous meltwater lakes along its rim. One of the largest, often called Lake Agassiz, sprawled over what is now central Canada, dammed in by ice and moraines. For long stretches of time, its outflow was routed southward, through the interior of the continent, toward the Gulf of Mexico. At some point near the onset of the Younger Dryas, those drainage routes may have changed. An ice dam could have failed, a low divide could have been overtopped. In several reconstructions, a massive pulse of cold, fresh water suddenly spilled northward instead, racing into the North Atlantic. Modern ocean circulation in that region is driven in part by the formation of dense, salty surface waters that cool, sink, and help power the Atlantic conveyor, a looping pattern that floods that surface with fresh meltwater, and the density drops. The water resists sinking. The conveyor weakens or shifts. In climate models, this kind of disruption tends to cool the North Atlantic region rapidly, even as the rest of the world continues to respond to long-term warming. Sea ice can expand, storm tracks can move, winters over nearby continents can become more severe. Evidence for a meltwater rerouting comes from several sources: geomorphic traces of abandoned spillways, changes in sediment supply to distant ocean basins, hints of freshening in marine cores. Yet the exact timing and volume of the key outburst or series of outbursts is still actively debated. Some records suggest a single catastrophic flood, others imply multiple pulses spread over centuries, and not everyone is convinced that meltwater alone did the work. Alternative or complementary ideas have been put forward. Some researchers have suggested that feedbacks involving sea ice and atmospheric circulation could have amplified relatively modest changes in freshwater input. A smaller group has proposed more exotic triggers, including a comet or asteroid airburst that might have darkened the sky with dust and soot, affecting climate. That impact hypothesis remains controversial, many of its claimed markers are disputed, and several independent teams have not been able to reproduce key results. What most lines of evidence do agree on is the outcome: a sharp, regionally intense cooling in the North Atlantic world, lasting a bit more than 1,000 years, before ending just as abruptly. The ecological consequences were profound. In Europe, forests that had been marching northward and uphill turned back. Pine and birch that had colonized newly warmed ground retreated, replaced by shrub tundra and steppe-like grasslands. In some valleys, tree rings record stunted growth, narrow bands of wood marking years of short summers and long, stressful winters. In eastern North America, pollen records show a similar reshuffling. Plants that prefer warmer, moister climates lose ground. Cold-tolerant species regain it. In some regions near the former ice margins, tundra conditions reassert themselves for centuries. Frost, heave, and permafrost processes, which had been waning, revive locally, reshaping soils and slopes. These shifts cascaded through animal communities: herbivores that favored open ground, reindeer, saiga, steppe bison in Eurasia, caribou and some megafauna in North America, found renewed expanses of suitable habitat in certain areas. Forest-loving species had to track shrinking woodlands or adapt to more patchy cover. Predator ranges flexed in response to their prey. In some places, new mosaics of forest, scrub, and grassland created complex, edge-rich environments. In others, the landscape became more monotonously open and windswept. For human groups in those regions, the Younger Dryas was not just background climate noise, it altered the menu. Where mixed woodlands had supported a broad range of nuts, fruits, and forest game, colder, drier conditions could reduce plant diversity and change animal migration patterns. Rivers affected by changing snowmelt and seasonal freezing might shift their flood cycles. Lakes that had been biologically productive could become more strongly stratified or ice-covered for longer, affecting fish populations. Archaeological records from areas such as the eastern Mediterranean and the Levant hint at disruptions in settlement patterns around this time. Communities that had experimented with more sedentary lifeways and intensive use of wild cereals during a relatively warm, stable interval known as the Bulling-Olerode seam in some regions, to become more mobile again as conditions turned harsher. In other places, people doubled down, developing new strategies to coax reliability from a suddenly less reliable landscape. The details vary from region to region, and the data are patchy, but the timing of certain cultural shifts does appear to line up with the onset and the end of the Younger Dryas, suggesting that climate shocks and human innovation were tangled together. What stands out, from the perspective of deep time, is the speed. On a graph of the last glacial cycle, the Younger Dryas is a narrow notch, a thin, steep-sided interruption in the broader rise toward warmth. Yet in absolute terms, the cooling and its later reversal happened over spans that fit easily inside a human memory. In Greenland, some reconstructions suggest that local temperatures dropped by several degrees Celsius in a century or less at the onset, then rose by a similar amount at the termination. Imagine being born into a world where winter snows linger longer each year, where lakes refreeze sooner and thaw later, where the tree line on the surrounding hills creeps downslope slowly but relentlessly. Imagine your grandchildren hearing stories of a time when summers had been softer, when certain fruits were more common, when a nearby valley had held more trees. For many people alive during the Younger Dryas, climate change would not have been a distant rumor. It would have been something you could feel in your bones. Colder mornings, shorter growing seasons, game appearing in different places, ice returning where it had recently vanished. And then, just as abruptly as it had arrived, the cold relented. Around 11,700 years ago, the isotopic curves in Greenland bend upward again. Pollen records show forests surging back. Glaciers in many mid-latitude mountains resume their retreat. The North Atlantic conveyor appears to recover strength. The world slips decisively into a new state. This is the moment when climatologists often mark the beginning of the Holocene, the relatively warm, stable interval in which all of recorded human history would eventually unfold. The Ice Age, in the classic sense, was over. But what kind of stability had truly arrived? And what would it make possible for the forests, the grasslands, and for the people who walked among them? At first, the Holocene did not feel like a clean break with the past. If you were living somewhere around the North Atlantic, what you would have noticed is that the wild swings eased off. The brutal, flickering cold of the Younger Dryas softened. Winters were still winters, but less knife-edge. Summers lengthened just enough that trees could take another risk, sending roots a little deeper, spreading seeds a little farther. In the Greenland ice, the isotope lines stop zigzagging and trend steadily upward. In lake sediments across Europe and North America, pollen from grasses and tundra shrubs gives way, again, to birch, pine, hazel, oak. Tree lines creep uphill and northward. Permafrost retreats. Glaciers, once again, resume their long withdrawal. Climatologists draw a boundary here, about 11,700 years ago. On one side is the late glacial world, with its abrupt swings and unstable ice margins. On the other is the Holocene, often described with a single word, stable. Stable, in this context, does not mean unchanging. It means something slightly subtler, that the wild, saw-toothed jumps of temperature and ice cover that had defined the last glacial cycle give way to smaller, slower undulations. The big levers, Earth's orbit, the tilt of its axis, the precession of its seasons are still moving, but they are now arranged in a way that favors relatively mild, ice-free conditions over the continents where most people live. If you could see a graph of global temperature over the last 100,000 years, the Holocene would look like a gently rolling plateau after a steep, chaotic climb. There are bumps, warmer centuries, cooler intervals, but nothing like the staggering drops and surges of the earlier glacial world. Yet global is an average, and averages can be deceptive. The new climate did not settle in everywhere at once, and it did not look the same in every region. In some parts of the world, the early Holocene brought a strengthening of the great monsoon systems. As northern summers warmed and the land heated more strongly than the surrounding oceans, seasonal low-pressure cells over Africa and Asia deepened. Moist air was drawn inland more vigorously. In many reconstructions, the West African monsoon pushed hundreds of kilometers farther north than today. Lakes swelled in what is now the Sahara. Rivers flowed through basins that are desert in the modern world. Hippo and crocodile bones turn up in places that now see only wind and sand. Farther east, in South and East Asia, monsoon rains also appear to have intensified in early Holocene millennia. Cave deposits, stalagmites slowly built, drip by drip, record changes in oxygen isotopes. But while some regions were getting wetter, others began drying out. In the subtropics and parts of the mid-latitudes, shifts in the position of the jet stream and the major storm tracks changed, who received dependable winter rains and who did not. Some areas that had been fed by glacial meltwater saw those supplies dwindle as the ice retreated up mountain and inland. Regions that had once sat beneath the margins of stormy polar fronts found themselves under more persistent high-pressure systems instead. Clear skies, more sun, less precipitation. Even within the same broad latitude band, local geography mattered. A mountain range could wring moisture from passing air masses on one side and cast a deep, dry rain shadow on the other. A coastline turned just the right way could either funnel monsoon winds inland or deflect them out to sea. Overlaying all of this was a longer, gentler arc in the Holocene temperature pattern, the approach to what climatologists sometimes call the early Holocene thermal maximum. Because of the way Earth's orbit was configured, northern summers in the several thousand years after 11,700 years ago received more solar energy than they do today. That extra sunlight did not push the planet into a runaway greenhouse. It was balanced by cooler conditions in other seasons in the southern hemisphere, but it did nudge average temperatures in many mid to high latitude land areas to a local peak. Exactly when this thermal maximum occurred and how strong it was varies from place to place. In some Arctic and subarctic regions, proxy records suggest notably warmer summers between about 9,000 and 5,000 years ago. Tree lines advanced into what had been tundra. Some high-mountain glaciers shrank to sizes smaller than their modern extents. Farther south, the signal can be weaker or shifted in time, blurred by local factors like lingering ice or nearby ocean currents. What people would have experienced, though, was not a single blazing moment of peak warmth, but rather a long stretch when the warm part of the year was a little warmer, the cold part a little less severe, and the boundaries between them slightly rearranged. Seasonality itself was changing. In many temperate zones, the combination of warmer summers and reliable moisture lengthened the effective growing season. The date of the last frost might have crept earlier in spring, the first killing frost in autumn might have arrived later, springs could be wetter, feeding flushes of plant growth, summers, in some regions, became both hotter and more thunderstorm-prone, punctuated by downpours that recharged soils. For wild plants, these shifts meant new opportunities. Trees that had been limited by short, cool summers could now complete their growth cycles more easily. Nut-bearing species like oak and hazel, once confined to refuges, expanded into broader ranges, dropping dense crops of calorie-rich food in mast years. Berry-producing shrubs colonized new riverbanks and forest gaps. Perennial grasses in certain regions put more energy into seeds, creating thick stands of edible grain-like heads along floodplains and valley bottoms. Animals tracked this abundance. Herbivores followed the green wave of spring farther each year. Migratory birds adjusted their timing to match new peaks in insect life and fruiting. River and lake ecosystems, freed from seasonal ice for longer periods, supported more fish and aquatic plants. For human groups, the landscape's calendar was being rewritten. There were new windows when particular foods were at their best, new routes and timings that made sense for seasonal movement. In some areas, the early Holocene may have felt like a kind of ecological boom time: more trees, more undergrowth, more animals, more predictable patterns of flowering and fruiting than in the turbulent late glacial. But stability, again, is relative. Even in this calmer climatic state, years were not identical. There were still droughts and flood seasons, cold snaps and heat waves. Monsoons could fail for a summer, or several in a row. Rivers could swell far beyond their banks under the right combination of snowmelt and rain. Volcanic eruptions could veil the sky with aerosols, dimming sunlight and depressing temperatures for a season or two. The Holocene's quiet contains its own record of surprises. Tree rings captured decades when growth stalled under stress. Lake levels rise and fall in layered muds, marking centuries-long wet phases and dry phases. In some regions, forest expansions are interrupted by charcoal layers, evidence of fire seasons that burned hard and far, resetting the vegetation clock. For the people scattered across this changing planet, the message was mixed. On the one hand, the huge, terrifying climate lurches of the last glacial period seemed to be behind them. On the other, the Holocene was not a climate you could ignore. It was a climate you had to read. You had to notice which springs were dry, which summers came early, how the winds shifted over the course of a lifetime. Over the next millennia, forests would reorganize, grasslands would take on new shapes, and the animals that depended on them would adjust or vanish. Human communities, in turn, would respond, not just by moving and adapting, as they always had, but by beginning to change the rules of the game, managing plants, guiding animals, reshaping the land itself. Before that could happen, though, the stage had to be fully set. The ice had retreated. The new Holocene climate was in place. Now the habitats of the world, forests, grasslands, wetlands and deserts, would begin their grand Holocene reshuffling, opening and closing ecological doors for every creature that walked, flew or swam through them. Forests were among the first to take advantage of the new rules. In the far north, where ice sheets had once sat like continents of frozen stone, the retreat left behind raw, scraped landscapes, bare till, meltwater ponds, unstable slopes. At first, only the hardiest pioneers could gain a foothold. Lichens, mosses, a scattering of herbs and dwarf shrubs. But as summers warmed and growing seasons lengthened, the colonists changed. Birch and willow crept in first, forming low, scrubby woodlands where, a few thousand years earlier, nothing but permafrost and glacial rubble had existed. Then came pine and spruce, marching northward and upslope, chasing the edge of the receding cold. Pollen grains buried in lake muds from Scandinavia to Siberia, from Canada to Alaska, tell the same broad story, trees flowing into space that had been locked in tundra for tens of thousands of years. The great steppe tundra that had stretched across the northern hemisphere during the glacial maximum, a mosaic of grasses, herbs, scattered shrubs, and frozen ground, began to fragment and retreat. In Europe and western Russia, forests pushed out onto what had been open mammoth steppe. In eastern Beringia, spruce forests crept across valleys once roamed by herds of grazing megafauna. This was not a gentle negotiation. Many grass and forb species could not tolerate deepening shade. Animals accustomed to wide sightlines and low vegetation, perfect for spotting predators and moving in large groups, found their world closing in. In some places, open steppe retreated to the driest ridges and interior basins. In others, it vanished altogether, replaced by continuous belts of woodland. Further south, in temperate latitudes, forests did not so much invade empty land as shuffle their own internal order. During the coldest parts of the last glacial period, many tree species had survived only in refuges, sheltered valleys, coastal strips, pockets of milder climate. With the Holocene, they began to pour out. Oak and hazel spread across Europe, chestnut and beech followed in some regions, each species moving at its own pace, depending on how easily its seeds were carried and how well it tolerated the new patterns of warmth and rain. Grasslands were not passive in this. In regions with drier summers or more pronounced seasonal droughts, the interior of North America, parts of Eurasia, sections of southern Africa, open grassland and savanna fought back, holding their ground against forest expansion. The balance between trees and grasses in these zones turned on a few key factors: rainfall, soil depth, grazing pressure, and one more element that became increasingly important in the Holocene: fire. Fire had always been part of Earth's story, but the Holocene rearranged its script. As forests grew denser and undergrowth thickened, the amount of burnable material on the landscape increased. Warmer summers, and in some regions, more frequent thunderstorms, meant more lightning strikes. Each bolt that hit a dry hillside or a resin-rich pine stand carried the potential to start a blaze. Charcoal trapped in lake sediments and peat layers shows pulses of fire activity as forests expanded. Some of these were likely natural lightning fires, racing through dry crowns and leaf litter at the end of hot summers. But over time, another ignition source became increasingly significant: people. Human groups had long understood that fire could reshape vegetation. Even late glacial hunter-gatherers used it to clear thickets, drive game, and encourage the growth of particular plants. In the early Holocene, as woods thickened and animals shifted their ranges, controlled burning became an even more powerful tool. In some regions, people appear to have used fire to hold back forests and maintain open grasslands, rich in grazing animals and seed-bearing plants. Regular burns could thin young trees, recycle nutrients, and favor fire-adapted grasses over shade-loving shrubs. Elsewhere, low-intensity burns may have been used within forests to promote certain understory species: berries, nut-producing trees, plants with medicinal properties. The result was a patchier landscape than climate alone would have produced: mosaics of woodland, savanna, meadow, and scrub, constantly adjusted by a combination of lightning and human intention. Fire regimes, how often, how hot, and how widely fires burned, shifted with every change in vegetation, and in turn pushed vegetation into new configurations. While forests and grasslands sorted out their boundaries, another kind of habitat was quietly spreading, especially in cooler, wetter regions: peatlands, where the ground stayed damp for much of the year. Poorly drained valleys, flat coastal plains, shallow basins left by retreating ice. Plants like sphagnum moss, sedges, and bog shrubs found ideal conditions. In these waterlogged environments, dead plant material did not fully decay. Oxygen was scarce in the saturated soils, and microbial activity slowed. Layer by thin layer, organic matter accumulated, forming peat over thousands of years. These bogs and fens became vast sponges embedded in the landscape. In northern Europe, western Siberia, Canada, and parts of Patagonia, peatlands expanded to cover hundreds of thousands of square kilometers. They stored enormous amounts of carbon that might otherwise have returned to the atmosphere as carbon dioxide. From a Holocene perspective, peatlands acted as slow, steady climate stabilizers, drawing down carbon as plants grew, locking it away in cool, wet ground. They also created new habitats, acidic pools rich in insect life, islands of dwarf shrubs and stunted trees, refuges for specialized birds, amphibians, and small mammals. For people, peatlands were both obstacle and resource, difficult to traverse. Rivers, too, were learning to live in a world without vast ice sheets feeding them. During the late glacial, many rivers had carried heavy loads of sediment from freshly eroding slopes and unstable permafrost. They braided across wide floodplains, constantly shifting between multiple channels. As vegetation took hold on hillsides and climates mellowed, erosion rates dropped. With less loose material to move, many rivers narrowed, deepened, and carved more stable single channels. Changing rainfall patterns added another layer of complexity. Where monsoons strengthened, rivers became more seasonal, rising dramatically in wet months, shrinking back in dry ones. In mid-latitudes with gentler, more evenly distributed precipitation, flows became smoother, with fewer extreme peaks. Elsewhere, the loss of glacial meltwater led to reduced base flows, forcing rivers to abandon some of their former beds and carve new, smaller courses. Floodplains adjusted in response. Old channels filled with silt and became oxbow lakes, rich in fish and wetland plants. New levees rose along frequently flooded banks. Periodic overflows spread fine sediments across valley bottoms, building up deep, fertile soils. Many of the world's great alluvial plains, the future breadbaskets of riverine civilizations, were being assembled, layer by layer, in these early Holocene millennia. As forests advanced, peatlands spread and rivers reorganized, animals followed or failed to. Species adapted to open, icy steppe found their ranges pinched between advancing trees and warming seas. Some managed to track pockets of suitable habitat northward or upslope, others fragmented into isolated populations, vulnerable to chance and local pressures. Still, others faded from the record entirely, part of the wider story of megafaunal loss that would play out unevenly across continents. At the same time, forest-dwelling and edge-loving species expanded. Deer, wild boar, and forest bison moved into the new woodlands of Europe. In North America, elk, white-tailed deer, and black bear took advantage of mixed forests and open glades. Beavers recolonized dammable streams, creating ponds that altered local hydrology and habitat patterns all over again. Bird communities shifted as well, woodland songbirds spreading into newly forested districts, waterfowl exploiting young lakes and wetlands, raptors adjusting their hunting strategies to new mosaics of cover and clearing. For human groups, these changes in habitat translated very directly into changes in subsistence. People who had once depended heavily on the predictable movements of large herd animals across open steppe had to rethink their strategies when those herds fragmented or vanished. In some regions, hunting turned toward forest game, more elusive, more solitary, requiring different tracking skills, different weapons, different forms of cooperation. In mixed forest grassland mosaics, broad-spectrum foraging became increasingly attractive. Nuts from expanding oak and hazel stands, berries from forest edges, fish from stabilizing rivers and lake shores, waterfowl from growing wetlands, small mammals and birds from a variety of niches, all of these could be woven into seasonal rounds of movement and harvest. On floodplains and in monsoon-fed valleys, stands of wild grasses and sedges, fattened by regular silt deposits, offered dense patches of edible seeds. In some places, people began to visit the same rich patches year after year, learning their rhythms, experimenting with small interventions that favored desirable plants and discouraged competitors. The reshaping of habitats in the early Holocene did not dictate a single human response. It opened a menu of possibilities, different in each region, each microclimate, each valley and coast. Some groups doubled down on mobility, tracking animals and seasonal resources across expanding networks of forest and plain. Others began to linger in especially generous places, reducing the distance between their camps and the foods they relied on. In the background, as forests grew and peatlands quietly sequestered carbon, the planet's climate system enjoyed an unusual stretch of relative calm. But the biological world was anything but static. It was reorganizing at every scale, from the composition of forests to the routes of rivers to the daily routines of human bands. Out of this ecological reweaving emerged a deeper puzzle, one that still draws debate today. As habitats changed and human pressures increased, why did so many of the great Ice Age animals disappear, while others thrived in the new Holocene world? To follow that puzzle, you have to zoom out in both space and time. The end of the Ice Age did not erase the world's big animals in one single global event. Their disappearances came in waves, at different times on different continents, against slightly different backdrops of climate and human arrival. In Africa, where our ancestors had lived alongside large animals for millions of years, the transition into the Holocene looks almost gentle by comparison. Many giants survived there: elephants, hippos, rhinos, giraffes, buffalo, great antelopes. Some species were lost, especially the most extreme cold-adapted or specialized forms, But there is no sudden cliff in the fossil record. Large animals had had a long time to learn what humans could do. Humans, in turn, had grown up in ecosystems dense with dangerous, unpredictable prey. In Eurasia, the story is sharper. Between roughly 50,000 and 10,000 years ago, the mammoth steppe unraveled, and with it, many of its signature inhabitants. The woolly mammoth, the giant deer with its enormous antlers, the woolly rhinoceros, cave lions, cave bears, and numerous large grazing and browsing species declined or vanished. The exact timing varies by region. Mammoths lingered in some high-latitude refuges much longer than in Western Europe. But if you stand back, there is a clear late glacial and very early Holocene thinning of the giants. In the Americas, the drop is even more abrupt. Humans arrived late there, sometime after about 20,000 years ago, and likely spread southward in pulses. Wherever they went, they entered landscapes packed with large animals. Ground sloths the size of elephants, giant beavers, short-faced bears, North American horses and camels, big cats and packs of dire wolves. By around 10,000, 11,000 years ago, many of these animals were gone. In Australia and nearby islands, a similar pattern had played out even earlier. Humans appear, and within a few thousand years, sometimes less, the continent's own megafauna, marsupial lions, giant kangaroos, enormous browsing wombat relatives, are reduced to memories and scattered bones. So what happened? One family of explanations points to climate. As the world warmed out of the last glacial maximum, temperature and rainfall patterns shifted rapidly. Ice sheets withdrew, sea levels rose, coastlines moved, and whole biomes migrated hundreds of kilometers in a few thousand years. For large animals with slow reproduction and specialized diets, this pace of change could be lethal. Lose your preferred grasses, lose your calving grounds, lose the frozen river crossings that structure your migrations, and each winter becomes a little more dangerous than the last. Another line of argument focuses on habitat change, the way forests pushed into former grasslands, the way wetlands formed and dried, the way fire patterns altered the balance between trees and open ground. Big grazers and browsers are not just large, many are picky about where and what they eat, and how far they can safely move between patches. Fragment the open steppe into islands of remaining pasture, and animals that once roamed in enormous herds can be bottled up into vulnerable pockets. Then there is us. As modern humans spread, they brought new hunting technologies, new strategies, and crucially an ability to coordinate over space and time. Spears thrown with atlatls, later bows and arrows, drives that funneled animals toward cliffs, swamps, or lines of hidden hunters. Perhaps even an increasing use of landscape fire to manipulate where animals fed and rested. In this view, megafauna were not slowly fading away until people added the final push. They were actively removed species by species, valley by valley, under a growing pressure of predation that they had no deep evolutionary experience with. Today, most researchers suspect it was not one cause acting alone, but a synergy. Climate stress and habitat rearrangement weakening populations, human hunting and disturbance finishing the job. The evidence for this complicated mix comes from several sources that together create a kind of multi-layered. Ancient DNA extracted from bones and teeth allows scientists to track genetic diversity over time. In some species, like the woolly mammoth, genetic data show long, gradual declines in diversity, beginning before the very end of the Ice Age, consistent with shrinking, fragmented populations stressed by environmental change. But they also show sudden local disappearances that line up closely with the first appearance of humans in those same regions. Kill sites add another layer. Scattered across Eurasia and the Americas are places where stone tools and butchered bones lie together, mammoth skeletons surrounded by spear points, bison trampled and piled as if driven into tight spaces. Some of these are clearly the remains of single hunts. Others look like repeatedly used locations where people returned season after season to intercept migrating herds. The number of such sites is not enormous, but their distribution tells a pattern. As humans learned the movements of big animals in new lands, they were capable of inflicting heavy, repeated losses. Then there is a more indirect witness, a fungus that lives in dung. Spores of certain dung-loving fungi are preserved in lake sediments and peat. When large herbivores are abundant on a landscape, these fungi flourish, shedding vast numbers of microscopic spores that settle into nearby waters and bogs. When big animals decline, the spores thin out. By counting them in layered sediments, researchers can reconstruct a rough history of grazing pressure. In parts of North America and Australia, these fungal proxies show a striking sequence. For thousands of years, high levels of spores indicate plentiful megaherbivores. Then, quite suddenly, the counts crash, often around the same time that archaeological evidence for humans appears. Shortly afterward, plant pollen in the same sediments begins to shift. Grasses decline, shrubs and trees increase, or fire-adapted species become more common, as if the entire vegetation regime is resetting in the absence of heavy grazing and trampling. This points to another dimension of the megafaunal mystery: what happened to ecosystems when the giants left. Large herbivores are not just passengers on the landscape, they are engineers. Their hooves break soil crusts, their grazing favors some plants over others, their dung fertilizes, their trails become channels for water and seed movement. Herds of mammoth and bison could keep shrubs in check, maintain open grasslands, and recycle nutrients rapidly through their bodies. Remove them, and everything else shifts. In some regions, the loss of grazing may have allowed woody plants to advance, thickening forests or shrublands where once there were open plains. In others, fuel built up in the absence of constant mowing and trampling, making fires larger or more intense when they did occur. Species that depended on open, closely cropped ground, certain grasses, forbs, and ground-nesting birds, would have retreated or vanished. Predators specializing in very large prey had to adapt to smaller targets or die out themselves. From this distance, with only bones, spores, pollen, and a few stone tools to go on, it is unlikely we will ever assign precise percentages, this much climate, this much hunting, this much habitat change, for each vanished species. What the pattern does suggest is that the end of the Ice Age was not a simple story of warming and relief. It was a time when small shifts in temperature and moisture cascaded through vegetation, fire, and animal populations, and when a new kind of hunter stepped into that unstable web. In some places, like Africa, long coevolution between people and megafauna may have cushioned the impact. In others, like the Americas and Australia, the meeting was sudden and the results catastrophic for the largest animals. For the human groups involved, these changes must have been both loss and opportunity. The disappearance of familiar prey forced shifts in diet and movement. At the same time, the restructuring of ecosystems opened niches for other animals and plants, some of which would become central to new ways of living. As big beasts withdrew into legend and memory, people found themselves moving across landscapes that were quieter, more wooded in some regions, more fire-prone in others, and increasingly shaped not just by climate and ice, but by their own decisions. The map of possibilities was changing again, and so were the routes people chose to follow. If you could have watched the end of the Ice Age from orbit, you would have seen the human story redraw itself on a planet whose lines were literally moving. As the ice sheets shrank back, they did not just remove obstacles, they opened some doors and slammed others shut. In northern Europe and North America, walls of ice that had blocked movement for tens of thousands of years began to split. Long, narrow, ice-free corridors appeared between retreating lobes of glacier. Meltwater cut valleys along their edges, carving routes that animals and people could follow into lands that had been under a kilometer of ice not long before. At the same time, the very lakes and rivers born from melting ice created new barriers. Huge proglacial lakes filled basins scoured by glaciers, cold inland seas with treacherous shorelines and unpredictable outburst floods. Ice-dammed lakes could rise quietly for centuries, and then, in a single catastrophic event, burst their barriers and send walls of water racing across the lowlands. Paths that had been safe one generation could become lethal or impossible the next. Farther south, the changes were just as dramatic, but subtler from a great height. Forests marched northward behind the ice. Grasslands shifted, wetlands appeared where none had been. For the groups living on the ground, this meant that familiar seasonal rounds needed constant editing. The valley where your grandparents always hunted caribou might now be a string of lakes. The open plain your parents crossed each year could be filling with scrub and young trees, better habitat for deer than for mammoth. People responded by moving, but not in one single, coordinated migration. Different regions tell different stories. Along the coasts, new possibilities appeared. At the height of the Ice Age, sea levels had been more than 100 meters lower than today. The continental shelves were dry land broad plains, stretching far out from the present shoreline. When the ice melted, the ocean rose, slowly but relentlessly, day after day, year after year. Shorelines crept inward, islands fused with mainlands, then detached again in new shapes. Rivers shortened as their mouths were drowned, turning into estuaries and bays teeming with fish and shellfish. For mobile hunter-gatherers, these coasts were magnets. Kelp forests, tidal flats, and estuaries can deliver food with a reliability that big game on the interior plains never quite matched. Shellfish, fish runs, seabirds, sea mammals, each required its own knowledge and techniques, but once mastered, they offered a rich, varied diet. Some researchers think that one of the great human dispersals at the end of the Ice Age followed a route like this. People moving along the edges of the Pacific, skirting glaciers in boats or on foot across exposed shorelines that are now far underwater. If that kelp highway model is close to the truth, then much of the evidence for it is gone. The campsites, fish processing spots, and landing beaches of these coastal pioneers would now lie tens of meters below the modern sea surface, buried in marine sediments. This is one of the deep frustrations of studying humans at the end of the Ice Age. The very process that opened new worlds to them has quietly erased much of their trail. Rising seas did not just nibble gently at the edges of continents, they flooded whole lowlands. In northern Europe, what is now the North Sea once held a vast plain connecting Britain to the continent, an area archaeologists call Doggerland. It was a landscape of rivers, lakes, and rolling hills, home to red deer, aurochs, and people. As the Holocene warmed, the North Atlantic advanced across it. Generation by generation, hunting grounds, campsites, and sacred places would have been swallowed. Oral memories may have preserved this, as stories of lands lost to the sea long after the last dry hill became an island and then a shoal. Similar drowned worlds existed off the coasts of Southeast Asia, where the Sunda Shelf once linked many of today's islands to the Asian mainland, and off the shores of the Americas and Africa. Everywhere the seas rose, they both enriched and displaced. New shallow water fisheries bloomed atop what had once been coastal plains, but families who had lived for centuries in one spot would have had to move inland or along the retreating shore, carrying their stories and inland routes remained vital. In the newly deglaciated interiors of North America and northern Eurasia, bands tracked the retreating ice and the animals that travelled with it. Herds of reindeer, bison, and other grazers followed fresh pastures along the glacial margins. Human groups shadowed them, learning the new lay of the land, where rivers now cut across old paths, where lakes blocked former passes, where stands of birch and pine offered shelter and firewood on what had once been bare, wind-scoured ground. These interior travellers relied on a different suite of skills. They needed clothing tailored for sudden cold snaps and wet, slushy snow. They needed portable shelters that could be assembled and taken down quickly as herds moved. They used toolkits that could be repaired and repurposed on the fly, composite weapons with replaceable stone points, bone needles, scrapers, drills, and awls that could convert animal hides and sinew into almost anything: boots, mittens, packs, tents. On the coasts, another set of technologies came to the forefront. Simple dugout canoes, hide-covered frames, log rafts, perhaps more refined watercraft in some regions. These made it possible to fish offshore, to cross rivers swollen with meltwater, to hop between islands, to reach places that had been utterly inaccessible when ice pressed against the shore. Even modest boats multiplied the distance a small group could realistically cover in a season, and gave them new ways to store and move excess food. Storage itself became a quiet revolution of this period. As salmon runs became predictable, as herds followed more regular routes, people experimented with drying, smoking, freezing, and burying food in cold ground or underwater. Pits lined with stone or bark could hold nuts, roots, and dried meat through a lean season. In cold regions, caches of frozen food were left in snow or permafrost, marked by memory and landmarks. These techniques were not new in the strict sense. Humans had stored food before. But the unstable climates and shifting resources of the late glacial and early Holocene made flexible storage strategies more valuable than ever. Underneath all these differences, one common thread stands out: adaptability. Instead of a single narrative of humans marching north or humans fleeing the flood, the archaeological and genetic evidence points to a patchwork of regional stories. In some places, like the interior steppes of Eurasia, people remained highly mobile, big game hunters for a long time, adjusting their routes but not yet their fundamental way of life. In others, like parts of the eastern Mediterranean or coastal China, groups began focusing more intensely on fish, shellfish, and plant foods, laying the groundwork for very different futures. In some valleys, rising seas were a distant rumor, and the main drama was the encroachment of forest onto open hunting grounds. In others, the ocean itself was the central actor, creeping closer year by year, transforming familiar landmarks into islands and bays. What ties these scattered stories together is not a single path, but a shared set of responses. The willingness to move, to experiment with new tools and clothes and boats, to reweave social ties as neighbours became distant and strangers arrived from over the horizon. As the map of ice and ocean shifted beneath their feet, people were already learning to bend with it. That flexibility would soon be turned toward an even more radical experiment, changing not just where they lived, but how they got their food in the first place. For most of the Ice Age, getting food meant moving. You followed herds, tracked ripening seasons, and shifted camp when the local berries were gone or the fish moved on. The landscape was a calendar, and survival meant reading it well enough to stay slightly ahead of hunger. As the Holocene climate settled, that calendar started to look a little different. Not perfectly stable, there were still bad years, droughts, freak storms, But in many regions, the wild swings of the late glacial period softened. Winters became less extreme, growing seasons lengthened, rainfall patterns, while still variable, grew more regular in some river valleys and coastal zones. That increased predictability changed what was possible. If you know that every spring the salmon will pour into this river, or that every autumn these oak groves will drop acorns, you can plan more than a week or two ahead. You can arrive early, build more permanent shelters, coordinate with neighboring bands, and bring containers and tools optimized for that one resource. You can start to think in terms of a schedule. Archaeologists call this kind of planning intensification. Instead of living mostly off a few high-value foods, mammoth, bison, reindeer, people began to broaden their diets dramatically. They added more fish, more shellfish, more birds, more small game, more nuts and seeds and roots. It wasn't that they had never eaten these things before, they had. But now they leaned into them, designing an entire year's movements and labor around harvesting a wide range of foods as efficiently as possible. Picture a yearly circuit tied not just to one big hunt, but to a chain of peaks. Spring fish runs in one valley. Early summer greens and small animals in the uplands, late summer berries on the slopes, autumn nuts and grains along the river terraces, winter hunting in the forest or on the frozen lakes. Each stop required its own knowledge. When the first fish appeared, how to find the fattest shellfish, how to smoke or dry meat so it wouldn't spoil. This seasonal scheduling of resources meant that food was no longer just something you found, it was something you organized. Storage became the quiet partner of intensification. If the acorns always drop in late autumn, and you can predict roughly how many you'll get, it makes sense to gather not only what you can eat that week, but as much as you can carry and process. You leach out the bitterness, dry or roast them, and tuck them away in pits or baskets for winter. In many late Ice Age and early Holocene sites, archaeologists find clusters of storage pits, sometimes lined with stone or bark, dug into the same spots year after year. They see layers of charred seeds and nutshells, fish bones in heaps, masses of small animal remains. These are the fingerprints of people who had started to build food surpluses into their way of life. Surplus is never just about calories. Once you can reliably produce more than enough at certain times of year, you can trade, you can host visitors, you can hold rituals with special foods, you can support specialists who spend more time on tools or art or leadership and less on daily foraging. New food economies quietly rearrange social possibilities. In some parts of the world, especially along coasts and big rivers, the combination of predictable resources and better storage led to something even more radical: semi-permanent settling. If the salmon are always here, if the shellfish beds replenish, if the nearby wetlands reliably produce reeds, ducks and tubers, why drag your home hundreds of kilometers? Why not stay most of the year near the richest spots and send small parties to range out when needed? But intensification didn't automatically mean farming. For a long time, people remained expert foragers who simply squeezed more from the landscapes they knew. The boundary between foraging and farming is fuzzier than it appears in schoolbook timelines. Long before full agriculture, people were already nudging plants and animals in their favor. They weeded around favored wild grasses and tubers. They burned patches of forest to encourage fresh growth for game and for edible plants. They scattered seeds near camp, intentionally or not, from the contents of their stomachs and trash heaps. They spared young fruit trees while cutting others for wood. They might have transplanted useful plants closer to water or to camp, or protected patches of shellfish from overharvesting. In places like the Near East, East Asia, Mesoamerica, and parts of Africa, we see hints of this management thousands of years before the first clearly domesticated crops. Wild wheat and barley in the Levant, wild rice in China, teosinte in Mexico, sorghum and yams in Africa. People were harvesting them intensively, processing them with grinding stones, and returning to the same stands again and again. Were they consciously cultivating these plants, or simply taking advantage of naturally rich stands and accidentally favoring more human-tolerant varieties over time? The evidence is delicate, and that's where the uncertainty comes in. Much of what we know about early plant use comes from tiny traces: seeds charred in ancient hearths, grains trapped in the crevices of grinding stones, microscopic starch granules clinging to stone tools, pollen in lake sediments. Interpreting these clues is more like forensic work than like reading a clear inscription. A handful of wild cereal grains at a site could mean people were intensively harvesting them, or it could mean someone tried a new food once. Grinding stones might have been used for seeds, or for pigments, or for bone. Starch grains can tell us that certain plants were present, but not exactly how they were managed. Different researchers read the same fragments and see different stories. Some argue that active cultivation, sowing seeds, clearing competing plants began surprisingly early in several regions. Others suggest that for a long time people were mainly brilliant opportunists, shaping landscapes with fire and choice, but not yet locked into the labor demands of true farming. What seems increasingly clear is that there was no single birthplace of new food economies. Instead of one cradle of agriculture, we see multiple centers of intensification and management, each with its own tempo and trajectory. In the Near East, communities leaning heavily on wild cereals eventually crossed a threshold into cultivating and domesticating wheat, barley, and pulses. In Eastern Asia, people focusing on wetland plants seem to have steered wild rices and millets down their own path. In the Americas, maize evolved from a wild grass under the hands of generations of experimenters. In New Guinea, highland gardeners worked with taro, yams, and bananas. Elsewhere, in parts of Europe, Northern Asia, and the Americas, groups built rich, complex societies while remaining primarily hunters, fishers, and gatherers, using storage and scheduling rather than crops as their main strategies. All of these were food economies in the making, ways of organizing knowledge, labor, and landscape, not just ways of filling stomachs. From a sleepy distance of thousands of years, it's tempting to see the birth of agriculture as a single turning point. One day, everyone was hunting mammoth, the next they were sowing fields. The real story is slower and more tangled. People learned to read their newly more predictable environments, stretched their seasonal calendars, broadened their diets, and began quietly shaping the plants and animals around them. By the time we reached the first true villages, with houses clustered year-round and fields encircling them, those villagers are inheriting choices made over countless generations. Choices about what to eat, where to stay, and how to make the landscape more reliable than the Ice Age world had ever been. Those choices start to look very different once you stop thinking in terms of a camp and start thinking in terms of a place. For most of human history, home was wherever your group happened to be this season. The hearth, the tools, the songs, the people around you, that was the constant. The geography changed. As the Holocene wore on in a handful of regions, the geography started to stay put. In the Near East, along the Euphrates and in the hills of the Levant, on the coasts of the Pacific Northwest, around rich wetlands in China, along the Nile, the Danube, the Rhine, in Japan's shell-mound villages and in early sedentary sites along the Peruvian and Chilean coasts. Different climates, different foods, but the same quiet revolution. People began to build in ways that assumed they would be back. Not just next season, but next year, and the year after that. At first, this might look like slightly sturdier huts, post holes dug a bit deeper, hearths rebuilt on exactly the same spot. Then you start to see something more. Clusters of houses that are rebuilt over generations, thick layers of debris and rebuilding stacked one on top of another. Whole hills made of old houses and garbage rising slowly out of the plain. Archaeologists call these tells. To the people who made them, they were simply where their grandparents had lived and where their grandchildren probably would. A permanent or semi-permanent settlement changes what you can do with food. Storage pits become bigger, more numerous, sometimes lined with stone, plaster, or basketry. You can build granaries or storage rooms raised off the damp ground. You can keep heavy grinding stones in one place instead of dragging them around the landscape. And once you can store large amounts of food in fixed locations, new questions appear. Who controls the storage? Is it a household, an extended family, a ritual leader, some kind of council? Who decides when the grain is opened, or who gets how many dried fish, or whose baskets go into the best, driest pit? Property begins to crystallize around these decisions, not necessarily in the modern sense of deeds and fences, but in the sense of recognized claims. This roofed space is my family's. That plot of tended plants is ours. These jars of grain belong to that household, not to everyone passing through. The archaeological signs can be subtle. Repeated rebuilding of houses on the same footprint, separate storage areas, clearly associated with particular dwellings, differences in house size and construction. But they all point toward a new social landscape, where mine, yours, and ours needed careful negotiation. Yet even as some groups began to anchor themselves more firmly to particular places, movement didn't disappear. It changed scale. Many early villages seem to have been seasonal magnets. At certain times of year, people from scattered camps and small hamlets converged on one rich spot, a salmon river, a nut grove, a lakeshore full of waterfowl, a pass where herds predictably. Food was processed on an industrial scale, and at the same time, marriages were arranged, disputes settled, alliances renewed, stories exchanged, rituals performed. We can glimpse this in places like the Natufian sites of the Levant. where substantial stone-built structures sit amid dense clusters of burials and storage pits in the shell-ring villages of Jomon, Japan, where generation after generation feasted on seafood and left their middens as monumental arks, in the cedar plank villages of the Pacific Northwest, where rich fisheries underwrote big, complex communities that still relied on wild resources. These were worlds organized as much around gatherings as around daily subsistence. Shared gathering sites demanded coordination. If dozens of groups were arriving at the same river bend or hilltop, someone had to decide where to place the hearths, where to dump the waste, how to keep the peace. Out of this need for coordination, something else grew. Monuments and ritual spaces. Long before stone circles like Stonehenge, people were marking off special places within or near their settlements. In the Near East, sites like Göbekli Tepe and later ritual buildings at Çatalhöyük show massive communal investment. Carved stone pillars, enclosed rooms covered in plaster and paintings, installations that were clearly not ordinary houses. In Europe's Mesolithic, large timber structures and defined open spaces suggest gathering grounds for ritual or decision-making. In the Americas, early mound complexes began to reshape flat floodplains into stepped, elevated spaces that were clearly meant to be seen. These constructions tell us a few things at once. They imply surplus, enough food available, regularly enough, that some people could spend many days hauling stone, cutting timber, or plastering walls instead of chasing game. They imply planning, coordination of labor, agreement on design, shared ideas about what the finished space should mean, and they hint at new kinds of authority, individuals or groups who could persuade others that this project, this place, deserved their time and effort. Were these the first chiefs, the first priests? The evidence is messy, and scholars argue about it. Some researchers see early sedentary communities as the cradle of inequality. Larger houses, richer burials with special goods, concentration of storage in certain buildings, these are read as signs of emerging elites, people with more power, more prestige, or better control over food and ritual. Others point out that wealth and status don't always map neatly onto political domination. A grave filled with ornaments might mark a beloved storyteller, a healer, or a child given special attention, not necessarily a ruling class. Many early villages show repeated rebuilding in similar forms, suggesting continuity rather than dramatic hierarchies. In some coastal and riverine societies that remained foragers, status might have been highly visible during feasts and potlatches, yet power could still be fluid and contested. The truth may be that early villages experimented with many different social arrangements. Some may have drifted toward more rigid hierarchies, then collapsed or rebalanced. Others may have deliberately held onto egalitarian norms, using ritual gatherings and gift exchanges to prevent any one lineage from locking down control of land and storage. What the archaeological record does support cautiously is a strong link between environmental stability, resource concentration, and community growth. Where the Holocene climate made certain spots especially predictable, river valleys with flood-fed soils, coasts with reliable upwelling fisheries, wetlands that buffered drought, people could stack bets in their favor. Those places invited investment: terraces, irrigation ditches, house platforms, storage buildings, shrines. Each new layer of investment made it harder to leave and more attractive for others to join. Over generations, the world that had once been a loose mesh of small, mobile bands became increasingly dotted with nodes, villages, ritual centers, gathering sites that exerted a gravitational pull on surrounding landscapes. In those nodes, people had to answer new questions. How do you live with hundreds of neighbors year after year? How do you share water, fields, and fish runs? Who speaks for the village when it makes a promise or a threat? The end of the Ice Age didn't just thaw glaciers and raise seas. It pulled humans into tighter knots of cooperation and conflict, into settlements where memories could pile up like house floors and where stories could attach to specific doorways and stones. Those knots, those early villages, are where our familiar social worlds begin to take shape. Families and neighbors, leaders and rivals, insiders and outsiders. And as the climate's new rhythms sank in, people began to weave those experiences into something else that would endure long after the first houses rotted away, stories about what it meant to live through a world transformed. Those stories almost always start the same way. The world is as it ought to be. People know their place. The animals know theirs. The sky does what it's supposed to do. And then the water starts to rise. Sometimes it's rain that refuses to stop, falling for days, weeks, years. Sometimes it's a sea that swallows the shore, a river that leaps its banks and never quite goes back, a wall of water that appears with no warning at all. Sometimes it's framed as punishment, sometimes as mistake, sometimes as pure, indifferent catastrophe. What's striking is not that one culture has a story like this, but that so many do. Along the Tigris and Euphrates, ancient Mesopotamian texts describe Utnapishtim, warned by a god to build a great boat before a flood wipes out humanity. In later Hebrew tradition, that story becomes Noah. In India, one version tells of Manu saved by a talking fish who urges him to build an ark before the waters rise. In parts of Greece, Deucalion and Pyrrha survive a deluge that drowns the rest of humankind. In parts of China, myths speak of relentless floods that only end when channels are cut and the waters are tamed. Across the Pacific, in Polynesia and Aotearoa, there are tales of canoes that ride out a world flood. Among many indigenous groups in the Americas, from the northwest coast to the Amazon basin, stories remember a time when the waters covered the land and people survived by clinging to rafts, mountains, or trees. You could spend a lifetime mapping these narratives. Some are brief and stark. Water rises, the world is destroyed, a few survivors repopulate it. Others are intricate epics filled with named places, specific hills and rivers and bays. It's tempting to draw a straight line from those stories back to the actual seas that rose at the end of the Ice Age. Between the glacial maximum and the Middle Holocene, global sea level climbed on the order of 120 meters. Shelves that had once been dry plains drowned. Coastal valleys turned into fjords and estuaries. Islands appeared and disappeared. In some places, the shoreline retreated slowly, year by year. In others, ice-dammed lakes burst or unstable slopes collapsed, sending sudden surges of water down valleys and out across lowlands. Standing on one of those coasts, generation after generation, you would see the world changing in ways that were hard to miss. Old campsites on the shore would have to be abandoned. Oyster beds that your grandparents harvested might now be out beyond safe wading depth. Grave sites, sacred rocks, fishing weirs, features tied to stories, could end up beneath the waves within a few human lifetimes. Archaeology gives us glimpses of this drowned world. Off the coasts of Europe, side-scan sonar and underwater excavation have revealed Mesolithic landscapes now under tens of meters of water, peat layers with preserved tree stumps, stone tools, hearths, even traces of paths. Doggerland, the now submerged plain that once linked Britain to continental Europe, is probably the most famous. What is now the North Sea was once a patchwork of rivers, marshes, and low hills, inhabited by people who hunted, fished, and gathered there for thousands of years. As the ice sheets melted and global sea level rose, that plain shrank and finally vanished beneath the waves. In the Black Sea region, some researchers have proposed that a relatively rapid flooding of a low-lying basin, perhaps through the Bosporus, could have created dramatic local effects. Shorelines racing inland, villages displaced, oral memories of a sea that suddenly expanded. Around the Mediterranean and in parts of Southeast and East Asia, there are reports of submerged structures, what look like walls, terraces, or platforms now lying below modern sea level. Some of these features probably are human-made: fish traps, boat landings, foundations of coastal buildings. Others may be natural formations that happen to resemble architecture. Sorting one from the other is painstaking work, and interpretations shift with each new survey. All of this makes an obvious story easy to tell. People watched their coasts disappear, remembered it as a great flood, and passed that memory down for thousands of years until it was written into myth. But human memory doesn't work like a camera. Oral tradition is not a fossilized recording of a single event. Stories change in the telling. Details are added or dropped, catastrophes from different times blur together. This storm, that tsunami, the year the river froze and then broke all at once. A story first told to explain why the old shell mound is underwater might, 100 generations later, become a moral lesson about why people must keep the proper rituals, or a political charter explaining why a particular lineage has the right to rule. Scholars who study myth see patterns, but they don't always agree on what those patterns mean. Some argue that widespread flood motifs point to very ancient, shared experiences of post-glacial sea level rise, stitched into tradition and carried forward as people moved and cultures split. In this view, the recurrence of certain themes, divine warning, a chosen survivor, a boat or high mountain, a new world emerging from the waters, is a kind of cultural fingerprint left by real environmental upheavals. Others caution that water is such a universal force in human life that you don't need a single deep historical event to explain these similarities. Almost every settled society lives near rivers, lakes, or coasts. Floods are common, often devastating. They lend themselves naturally to metaphor, cleansing, punishment, renewal, chaos, and order. Given those ingredients, it's not surprising that different cultures might independently invent stories of a world flood without any direct memory linking back to specific post-Ice Age shorelines. There are more radical possibilities too. Some researchers suggest that certain traditions might preserve surprisingly precise information about now submerged landscapes, named reefs, channels, and former coastal plains that match bathymetric maps. Others think that resemblance between ancient place names and underwater features is coincidence, or the result of our tendency to see patterns where none exist. So where does that leave us? Perhaps with a more modest but still remarkable idea that human communities have always tried to make sense of environmental change by turning it into narrative. When the river cuts a new channel through your fields, it's not just erosion, it's a story about why the river chose that path. When an earthquake sends a wave over the village, it's not just plate tectonics, it's a story about angered spirits, or the time the world nearly ended. When the shoreline keeps creeping inland, year after year, it becomes a story about an age when there was more land out there, when the ancestors walked where only fish swim now. Some of those stories might carry dim echoes of the great Holocene sea level rise. Others may come from later storms, from landslides, from local dam breaks and unexpected tides. Over time, they fold into each other, layered like the floors of old houses in a tell. What they preserve, more reliably than any specific date or depth, is a sense of vulnerability and resilience. The knowledge that the ground under your feet is not guaranteed, that water can erase familiar places, and that communities can sometimes survive and make a new world afterward. As you listen to these flood myths from tablets and scriptures, from elders sitting by fires, from stories still told along coasts and rivers, you're hearing more than entertainment and more than garbled geology. You're hearing one of our oldest ways of remembering that the world can change faster than we expect. How much of that remembrance reaches all the way back to the end of the Ice Age, and how much belongs to more recent storms may be a question we can never fully answer. But it leads to another one, closer to home. When our own coasts shift, when seas nibble at cities and salt creeps into fields, what stories will we tell about it? What fragments of today's lived experience will someone, thousands of years from now, still be whispering as they drift off to sleep, trying to remember what it felt like when the waters began to rise? Because the thaw didn't just reshape the land, it gave us a template for how to remember and how to forget, a world transformed. By now, the pattern might be starting to feel familiar. The end of the Ice Age wasn't a clean break, a single sunrise when everything melted and the world stepped neatly into the present. It was a long series of thresholds, a step forward into warmth, a stumble back into cold, seas that climbed in pulses, forests that advanced, retreated, and advanced again, animals that flourished in one phase and vanished in the next. Each swing carved a little more deeply into the map of the planet and into the possibilities of human life. As the great northern ice sheets shrank, they didn't just reveal bare rock. They uncovered new river systems, new lakes, new corridors between regions that had been sealed off for tens of thousands of years. Where tundra had once stretched unbroken, patches of birch and pine began to appear. Grasslands pushed into what had been desert, wetlands formed in old meltwater channels. For plants and animals, this meant opportunity and danger in equal measure. Species shifted their ranges, tracking the climates they preferred. Some kept up, others couldn't. The mammoths and their megafaunal companions were only the most dramatic casualties of this reshuffling. For humans, the same upheaval opened doors. People followed the game and the edible plants into freshly exposed lands. They learned new coastlines, new fishing grounds, new migration routes. They invented ways to live in dense forests, to manage wetlands, to coax food from increasingly predictable seasons. They domesticated plants and animals, not everywhere at once, but in scattered pockets where climate, landscape, and cultural traditions lined up just right. Over a few thousand years, an eye blink in geological time, the world's human economies diversified from almost entirely hunting and gathering to a patchwork of foragers, herders, gardeners, and farmers. Villages appeared, then grew. Social hierarchies thickened, rituals multiplied, languages branched. The Holocene became not just a climate interval, but a human experiment, and yet even here, the story resists simple outlines. There are things we still don't know, and may never know with precision. We argue, for example, about how fast some of those sea level jumps really were in particular regions, and how directly they shaped migration and myth. We debate whether climate shifts were the main driver of megafaunal extinctions, or whether human hunting and habitat change tipped the balance. We revise timelines for when and where agriculture began, as new sites appear from under fields, cities, and seas. Every new ice core, every sediment layer drilled from a lake bed, Every ancient DNA sequence taken from a bone or a grain of pollen adds another small piece. Sometimes it confirms what we thought, sometimes it quietly contradicts it, nudging the whole picture into a slightly different shape. The end of the Ice Age, in that sense, is still ending. Its story keeps changing as our questions change, but some themes hold steady. Landscapes, we see, can respond very quickly to changes in temperature and moisture. Coasts can creep or leap. Forests can arrive within a few generations where none stood before. Rivers can abandon their old beds. Thin soils can blow away or build up. And human societies, large or small, have always had to adjust, moving, replanting, rethinking who they are in relation to the places they inhabit. Sometimes that adjustment looks like collapse, or flight, or loss. Sometimes it looks like ingenuity, new tools, new alliances, new stories that make sense of unfamiliar seasons. When we look back at the Great Thaw, we're not just watching ice disappear, we're watching the rehearsal for our own moment on the stage, a world in which climate can and does shift within the space of memory. And some of that remembering happens in scientific journals and databases. Some of it happens in songs, in myths of floods and fires, in quiet family stories about how the weather used to be. Listening across that whole spectrum, cores of ancient ice and tales told by grandparents, we hear echoes of the same insight. The ground is never as fixed as it feels, and yet life stubbornly goes on. As you drift towards sleep, you're sharing a thin slice of time with all those earlier watchers of the sky and sea. Hunters on retreating glaciers, fishers on drowning coasts, farmers reading the first reliable seasons. If you'd like to keep traveling through these long stories of Earth and humanity, you can gently tap like or subscribe so you don't miss the next journey. I'd love to hear where you're listening from and even what time it is there. So if you feel like it, leave a comment and add your place and your moment to this wider map of listeners stretched out across the night.